Now welcome the Provost for the University of Washington, Anamari Kause.
Hi, good evening, and welcome to the beautiful Pacific Northwest. It's spring outside, if you haven't noticed, and so everything's coming up roses for you. It's really my pleasure to welcome you all to the 39th Annual University Faculty Lecture. Every year, faculty members at the University of Washington choose one of their peers to give this distinguished lecture. And it's just about the highest honor that faculty can give to a member of their own. It was established in 1976, and it's included a very impressive roster of bold and visionary lecturers, from artists to historians to scientists and engineers. We've even had a few Nobel laureates. So it really is an august group to which we welcome Professor Lillian C. McDermott, who's our speaker for the evening. She's been a full-time member of the UW faculty since 1973, so one of the few people that's been here longer than I have. And a physicist by training, she has a PhD in experimental nuclear physics, and Professor McDermott has helped reshape the landscape of physics education. We all know how important science is, but we can't get to scientists without science education. And she leads the physics education group, which she helped establish when she joined the faculty over 40 years ago. This group uses a very research-intensive, inquiry-based approach to teaching and to learning physics. And it's renowned all over the world for its leadership role in physics education and in the preparation of physics teachers for tomorrow. And quite frankly, the whole world of science, not just physics, looks to the work that this group has been doing. Here at the University of Washington, we pride ourselves on providing our students with a real leading-edge student experience. Faculty and students alike will tell you that Professor McDermott has an unwavering passion for physics. And thanks to the undaunted work that she's done with her whole team, she's ensuring that students will have the kind of leading-edge learning experiences that we pride ourselves on for years to come. But aside from all of this, I've gotten to know Professor McDermott fairly well over the years. We've been good colleagues and weathered a number of storms together, as well as some good times. And I think it's important to know she's a bright, warm, inquisitive woman, and she has a passion for the arts. It's not like arts and sciences, it's arts and sciences, from Jane Austen to Mozart. She has a genuine curiosity for the world around her, and I can say undoubtedly that we're very lucky to have her here. So please join me in welcoming our university faculty lecturer, Professor Lillian McDermott.
Well, good evening, everybody. I am overwhelmed by the undeserved introduction, but it's over, and nothing I can do about it. So this is probably quite different from most of the other lectures that you've heard, because what we do is a little different. We are a group in the physics department, and we are engaged in helping students learn physics. And I'm going to give examples tonight. Don't panic. If you haven't had physics or haven't taken it for a long time, we have picked examples. We have picked. Peter Schaefer's been helping me, and we picked them together, examples that should be comforting, I hope. I'd like to begin by thanking everybody for the honor. It is a great honor to present the faculty lecture. And to everybody in the group, because everything that I'm going to be talking about tonight was not something that I did or that I did alone. I did it with others, and I've been very lucky. And I also want to mention one other group of people, and that's my family. Two of my three children are here, Bruce and Melanie. The third is in the UK. She would have come, but I thought, I've gone with her to some other things that maybe I could settle with one coming from New Jersey and one being here. And some of you, I think, knew my husband, Mark, who made a lot of efforts to give me the possibility of being able to work as hard as I did. So those are my primary thank yous. Of course, I have other thank yous, but these are the people that made made it more likely that I could do this. Now I'm going to put names up. There is no time. It would take a lot of time to read the name of everybody, but you can sort of scan it, and you can see that the current faculty consist of myself, Paula Heron, who's on sabbatical, and Peter Schaefer, who's here tonight. We have postdocs, and we have a K-12 teacher, Donna Messina, and I'll talk about our K-12 program as the evening wears on. And there are lots of other names, and all of them. By now, we've had something like 25 students get their PhD for research on the learning and teaching of physics, and that's part of tonight's story. The goal of our group is to improve the learning and teaching of physics from K-12 to the university level, and it goes from introductory to graduate level. But don't panic. We will not be discussing graduate level physics, so you can rest assured. How do we do this? I'm going to give illustrations, doing research on the learning and teaching of physics, developing curriculum that is based on that research, that is both research-based and research-validated, and I'll explain what I mean by that. And we disseminate our results, we report them in peer-reviewed journals, go to professional meetings, and we conduct workshops for K-12 teachers and university faculty. And most of what I'll be talking about tonight involves K-12 teachers and introductory physics students. We also consider it our mission to prepare graduate students and postdocs for their role as future faculty and for leadership in physics education research. That's who we are, and that's what we do. And now I should mention, what do I mean by discipline-based research on learning and teaching? It differs from traditional education research, in which the emphasis is on educational theory and methodology. And it focuses on student understanding of content in the discipline. In our case, it's physics. Discipline-based, in our case, is physics-based. And we believe, as has come to be accepted now by people more generally by people in physics, it's an important field for scholarly inquiry by science faculty in science departments. This is not to put down what's done in education departments, but in our particular case, the focus is understanding of the subject matter, and you can make analogies to biology and to other fields as well. So these references are just there, so you know that everything I'm going to talk about, everything I'm talking about has been published. The challenge in science education is the two parts that I'm going to discuss tonight are the preparation of K-12 teachers in physics and physical science and instruction of university students in introductory physics. And they don't require prior study of physics. That doesn't mean that you need to understand everything that's said at the moment it's said, but it should give you a sense that it's something you could understand without that much background, really. I'm not going to read this entire list, but most of us who've read the papers are well aware there have been a lot of attempts to address the problem of student performance in physics. The one that's being fussed about now is No Child Left Behind, the mandated standardized testing with penalties associated with the schools. That's part of the news. But all of these have come and they've gone. And I'll mention in passing, we have collaborated in the case of some of them, in the case of one in particular, with the Seattle School District. As long as the money was there from NSF, they were interested. Now there's nothing left that the city of Seattle does as for education that is citywide. And none of them have addressed the situation completely. And there's one of my favorite quotes: "Those who cannot remember the past are condemned to repeat it." And that's what we keep doing, keep repeating this particular one. So anyway, I like that quote. The national impact, there have been cycles of reform, they're short of expectations. In particular, post-Sputnik got everybody excited. We should do something about science understanding. We should do it through education. and many famous physicists got involved in helping design curriculum for K-12 teachers, really for K-12 students. The assumption was that K-12 teachers would learn along with their students. This is not what usually happens. It doesn't happen that way. And that the curriculum that the K-12 teachers are expected to teach their students is something they don't need particular extra help in. That's not true, and I'll try to show you that. So evidence from research, it's not shocking. What is taught is not what is learned. Most people probably know that to some extent. But here the analysis is, what are the reasons? There are reasons. Generally speaking, the curriculum and the students are not well matched. The teachers who are who were students and have gone to the university are not well matched to the curriculum that's used in the schools. And the students and the teachers are not. That's what the jagged the cut indicates. Now, yeah, I'm stumbling for words. Now, what is probably known by many of us, but not by all of us, is 65% of high school physics teachers did not major in the subject. In many cases, they may have had the introductory course, or they may have had a couple of years of physics, if they had it. But how did they have it? Usually in a lecture course that goes by very quickly with standard labs, which is not what they need to teach children. And they don't recognize what's hard. What's hard for them, necessarily, they don't recognize that they don't understand. It's not their fault. They didn't have a kind of education that they might have had. And the curriculum, as you can see, is mostly abstract. The problems extend to the university level. However, the curriculum and the faculty match. Not only do they match really well, but many faculty feel, I learned it, and I know what it means to learn it, and the students are like me. Well, actually, at most, 5%, at most 5 or 6%, at most, of the people who are in our major courses are going to stay in physics, at best. So the curriculum, the big difference is the faculty write the curriculum, it matches them. It's how they understand it now. And I have been in a situation, in many situations, of people who say, I can explain it to you. And they explain. But the person who learns the most from explaining is the explainer, not the person to whom it's explained. That has been my experience. It's usually top down, and it's usually, they don't say it this way, written for faculty, and they can, most students are not people who are like the faculty who teach them. And this is not bad, I'm just commenting. They're not going to learn in the same way. So the preparation, those who teach science, a lot of the things are important. They learn those, hopefully, in education courses. Classroom skills, methodology, motivation, a lot of things that have to do with the theories of knowledge, of learning, the acquisition of knowledge. But there are two critical factors, and that is discipline-specific knowledge, the concepts, in the case of physics, reasoning and representations. And they don't know how best to help students acquire that knowledge. They're usually not taught that. Emphasis by our group is on how physicists, and by extension other science faculty, although I don't know that much about other sciences, can promote the intellectual development required for effective learning and teaching of physics, and by extension other sciences. Now I want to give you an example. It's another example, it's a true life example in a while, but first let me tell you what the setup was. The setup was an interview modeled after Piaget's interviews on motion that he used for a different purpose, to characterize the intellectual stage of learning of students up to the age of 16. We gave similar tests to, test is not the right word, demonstration interviews to students who were greater than 16, older than 16, namely college students. And in particular, elementary school teachers and underprepared students in the EOP program, Educational Opportunities Program as it was called, and introductory students. student is shown the motion of two balls. Ball A rolls with steady speed, steady velocity, as you can see by these flash shots. Ball A rolls on a level track, okay, so it goes on forever. Ball B rolls up an incline, and it started up faster, and it passes ball A twice. Students are asked, they've seen this now, they've looked at it, do the balls ever have the same speed? If so, at what time or times? And these questions were asked in 45-minute interviews of this group of students, and they're asked this question, and as you can see, I've already said that, actually. Okay, 40% of the elementary teachers answered correctly, and 60% for students in introductory physics, many of whom had already studied this general topic. Incorrect response, typical. The balls have the same speed twice at the two passing points. They failed to recognize the balls have the same speed at only one instant. All right, I'm gonna give you an anecdote that goes with that. And that, in a sense, we can interpret that as confusing position and speed. The prevalence nearly the same before and after instruction in kinematics. That's what's sad. I mean, if you don't know ahead of time, maybe you learn something. Okay, this is a transcript from a speeding trial we were able to find. When I saw the sign, slowed to 40 miles per hour, that's the driver, I checked my speedometer and noticed in my rear mirror a car approaching very fast. I pulled to the right to allow it to pass. I proceeded to the crest of the hill, and Officer Haley motioned for me, and the car on my left to pull over. He said, I have been driving 40 miles per hour in a 40 mile per hour zone. Is there anything you want to add, Trooper Haley? And he says, no, Your Honor. In this case, we have the additional factor of a radar machine. The judge says, I have the certification for the August check, and it was working properly. This is what the officer says. And do you want to ask any questions, Ms. Cates? She was the driver. Yes, radar can only pick up one car at a time. Can it clock two cars at one time? No, it's only one at a time, the officer says. It would seem to me that it's possible that the radar picked up the car that was passing me. This is what she says, it's reasonable. Prior to the hill, we can't see over. We can't see over, the officer says. I pulled over to the right to encourage them, meaning him, whoever it was, to go past. The car was on my left, coming over the hill, passing me. All right, is it possible these two cars were side by side and there may be some confusion? No. As a practical matter in this case, what difference would it make? This is the judge. Remember, he's been to college and to law school. If the two cars were side by side, you were both speeding. And this is documentation. And this is from Massachusetts, where there's a good educational system, supposedly. And the driver says, the car was passing me. I was not speeding, and the radar picked up that other car. Perfectly reasonable. Well, I'm satisfied the weight lies with the Commonwealth in this case. I'll uphold the magistrate's decision. And this is, well, it says something. It really does, because, as I said, Massachusetts, assuming he was from Massachusetts, but he's a judge, that he had learned something in school. So now I'd like to go into something a little different, that's some relevant personal history that led to my perspective on teaching and learning and how we should teach physics and physical science to teachers and improve the instruction in large introductory courses. And some of these reflections are relevant to other sciences as well, but this was my history. Well, in 1959, I got my PhD from Columbia in experimental nuclear physics. I had graduated from a liberal arts, a women's liberal arts college at that time, and from Vassar in 1952. Then I became an instructor for a while in City College of New York, and then came to Washington State when my husband Mark accepted position at the UW. Now, this is where it is a little different. Anti-nepotism was strictly enforced in the state of Washington. I could not work at the same institution where my husband was, but I was an academic anyway. So I went to Seattle University. Priest interviewed me, and there was a full-time and a part-time job, and he suggested I choose a part-time job because of I had 3 children. So I thought, well, he's probably right. I probably should take a part-time job. Now, in emergencies, you could set aside the nepotism rule. So in 1967 to 1960 time, I was a part-time lecturer. On last-minute notice, I get a call from the chair saying, we don't have an instructor for physics 121 or whatever at the time. And in those circumstances, they could waive the nepotism rules. Now, in 1968, a physicist, a physics professor, nationally recognized and very much interested in teaching, came to the University of Washington from Amherst College to start a physical science course for pre-service teachers and write a book, The Various Language. He took that from a very well-known poem by William Cullen Bryant. I'm just mentioning that in passing. So, 1970, will the last one leaving Seattle turn off the lights? That was the Boeing bust. And so then I didn't have a job because I was part-time at two universities. So I went to see Arnold, who I never met before, and I volunteered. I said, can I help you teach your course? Never having taught teachers, it just seemed like it was physics anyway. So I developed, he was working in elementary school, and I offered, or he asked me, I don't remember, to do a course for high school teachers. And then I got the idea that there were teachers who had finished the elementary course, Arnold's course, and wanted to learn more physics, but they couldn't go into the introductory physics course. They didn't have the mathematics. So I made room for them. And we had high school teachers and elementary middle school teachers in the same class. What was nice about it is that the concepts are not exclusive to either group. And what would happen is the high school teachers, prospective high school teachers, would try to help the elementary school teachers. And you know what they would say? Don't tell me, I want to find out for myself. That was very, very good. They did part of our teaching for us. Don't tell me, think it through. And then we were working on, I began to work on worksheets that later became our curriculum. I'll talk about that later. So then I had a friend in biology who was very interested in helping students qualify for a medical career or a science career, Leonie Pitternick. And she said, you've got to do the same thing in physics. I said, yeah, we should do the same thing in physics. And by this time, we were known as the Physics Education Group. And so I developed a section of the course for students in the EOP program who weren't really like teachers, but nevertheless, they didn't have the background. And in 1972, Title IX anti-nepotism laws were declared unconstitutional, which was a break for me, I guess. And Arnold Ahrens had an offer from Woods Hole to go there, and in order to keep him there, a new position was created, and there was a competitive search for an assistant professor of physics. And so I competed and had my first physics talk, for which I was even more petrified than I am for this one. So that tells you something. At that time, I began research in physics education, 14 years post-PhD in nuclear physics. I began it because I was interested. And there was 3 strong physics graduate students, one of whom is here tonight, at that time. They had applied for the DA program. There was a DA program that Carnegie Mellon, I think, had developed, and they wanted to be college teachers, and this program was specifically for them. However, it got discontinued by the university. For whatever reason, it probably wasn't very successful. And I had read the clinical interviews that Jean Piaget, a Swiss psychologist, had conducted to assess stages of intellectual development, and he used tests and kinematics, not to see what students didn't understand for conceptual reasons, but to see whether or not they had reached certain stages of intellectual development. And so I suggested to David, who was the first of these people, these graduate students, that he conduct individual demonstration interviews. Demonstration, individual, person interviewing you for 45 minutes or so. And based on Piaget's motion tasks. They were too easy for university students. I then suggested that he develop more appropriate tasks. Unlike Piaget, our purpose was not to determine the stage of intellectual development, but rather to probe understanding of basic physics concepts and reasoning. So it also occurred to me, and it's obvious, I think, why, that you couldn't just tell people. Arnold told our faculty, and they didn't listen because he just told them, and it's not enough. So I realized that although he deserved to be understood because he had great insights, that they didn't pay attention, and that anecdotal evidence based on a few students is not regarded as compelling, even if it is very, very wise. It occurred to me that documentation of learning or not learning might make a difference in bringing about change, and I became inspired to conduct systematic research on the learning and teaching of physics. And a reason for including this, in a sense, I mean, I look back, nepotism was terrible. On the other hand, ultimately, something good for me came out of it, but that's not what I would like to promote. I don't think it's the way to go. Okay, so I recognize the need that if you do this, you need to report it in ways that are part of the culture. And you had to provide evidence. These difficulties were conceptual and reasoning among many students, and the language had to be familiar to physicists. It couldn't be a lot of psychological, the way it had to be something physicists would understand, and that's the language. And then published in journals they're likely or possibly will read, and in our case, it's been the American Journal of Physics. So what happened, as you can see from the diagram here, I said this already, the UW discontinued the DA degree, which was designed to prepare college faculty as college students. But these were among the best students in the department. 2 of them had gotten the highest grade on the qualifying when it was given. Therefore, there was no problem. They automatically got transferred into the PhD program, and those are the years they received the PhD. So at about this time, we became a de facto center for physics education research and K-12 teacher preparation. In 1984, you notice this in quotes, I commuted to the National Science Foundation in Washington, D.C. to help restart teacher preparation, which had been discontinued in 1982 by President Reagan because of the way I describe it, the MACOS flap, Man, a Course of Study, a biological program in the social sciences, and because some of the things that the Eskimos and other people who were in that, described in that program, were doing were not considered acceptable, not acceptable in our culture. So the idea was the government shouldn't be doing it. And then there were reports that came out about how terrible we were doing in the sciences, and NSF started becoming engaged again below the graduate level. And I was asked to come and help start teacher education there. So I commuted. Commuting meant coming home every 3 weeks for 2 or 3 days, and then going back and being in Washington in between. And at about that time, people started coming to visit us to see our courses for pre-service and in-service teachers. In case some of you don't know, in-service means people actually teaching. Pre-service means people who don't have a teaching degree. And now there are many groups in physics education research and a variety of universities, some of whom are listed there. And then again, I guess we thrived because this shows I was an assistant professor in '73, promoted to professor by '81. Paula Heron, who's on sabbatical at Marseille now, came as a postdoc in '95 and was promoted to professor in 2007. And Peter Schaefer, who started as a graduate student, weathered the whole business of moving up and became a professor in 2008. By 2015, approximately, probably a little more, of 25 graduate students have earned a physics PhD for research on the learning and teaching of physics. So that's how it has been. Now, I want to do some more quoting. As argued in 1933 by R.K. Rickmeyer in Physics is Physics, first article in the first journal published by the American Association of Physics Teachers, which is now the American Journal of Physics, Rickmeyer wrote that he agreed with R.A. Millikan, another famous physicist, that science is, I quote, a body of factual knowledge accepted as correct by all workers in the field. He then went on to say, without a reasonable foundation of accepted fact, no subject can lay claim to the appellation science. Then one must admit that in no sense can teaching be considered a science. That's his opinion. So However, findings from research in physics education contradict that interpretation. Many students encounter the same difficulties. Same strategies are effective with many students. The results are reproducible and generalizable beyond a particular course, instructor, or institution. Teaching can be treated as a science when student learning is assessed by specified intellectual outcomes. Results from physics education research can be a critical resource for systematic improvement in student learning. And notice what I say, K through 20 plus, that includes most of us. So the procedures of our group is we conduct systematic investigations, apply the results, develop instructional strategies to address what we find, assess their effectiveness through pre- and post-testing. The post-testing in our particular case is always under exam conditions on exams. The pre-tests are not, are given in smaller sections, and they are really for two reasons. One is to see where the students start, and the other is that the more perceptive students recognize when they see what they've done, how they're thinking. So that's another reason for them. We document our methods and results, and we report them. And that's characteristic of an empirical science, applied science. So this is what we do, and those are our procedures. And these are the methods we use. I've already alluded to those. The application, then what do? We do the research, we identify what they have difficulty with, we develop instructional materials, and we do this over and over and over again until it's reproducible. And then we send our materials to other places, colleagues at other institutions, pilot sites, and only when the results are consistent do we consider that we've made some progress. So, insights. Inadequacy of teaching by telling. It's been my experience that the one who learns the most from explanations is the one who gives the teacher, who gives the explanation, not the student to whom it's given. That's been my observation. Because I used to like to tell people, I'd save them the trouble. I'd tell them what the answer was. Well, that doesn't do it. And that if you want to know where the students are, you have to keep your mouth shut for a while and listen. And the failure of our standard introductory courses to help teachers develop the depth of understanding they needed to guide the learning of others. Certainly our basic physics course, which is all, at best, most K-12 teachers have, won't do that. And that you need to ask qualitative questions, not questions for which formula did you use to get the right answer. So the trouble is, if you're good enough in math, you mask underlying problems to get your way around them. So qualitative questions that reveal basic conceptual and reasoning difficulties among underprepared students. And that was interesting. We had these EOP students. They lack some of the vocabulary and memorize formulas. But you know what? We got the same, when we asked qualitative questions, they tipped us off. Because when we asked the same qualitative questions of our course for majors or for engineering students, we got a lot of the same responses. So this was very, very useful, and it's interesting. Qualitative questions, the right kind, are really harder. And how should we teach teachers? I feel, I'm not the only person, but many of us feel teachers need the opportunity to learn or relearn, because often relearn, a topic in a way consistent with how they are expected to teach. Otherwise, they will imitate whoever teaches them and get up at best and chat and talk. And the concepts, reasoning skills, and representations should be taught together in a subject that's coherent, not just a little here and a little there. And so that inspired us to take an instructional approach that we consider guided inquiry. Namely, it's not just any. See, lots of times people think teaching by inquiry is, throw the lab material out and let them inquire. So they play. But if you know what you're doing, you can give the experiences the kind and get them to reflect on them that will help them come to where you'd like them to be. So physics by inquiry is the first of our two major curricula. It's teaching by questioning, not by telling. And that means that the person who does the teaching has to be skilled enough to ask the questions that will have the students arrive at their the conclusions by themselves. So I'm going to give some examples. And here are some examples from physics by inquiry, namely in courses that are not yet, or I shouldn't say yet, that maybe that's not right, are not at the introductory level. So here is a Piagetian task given to primary teachers and students in introductory physics. Student is shown two balls of identical size and shape. One's made of aluminum, the other of iron. Students observe that the water rise when the aluminum ball is placed in cylinder 1, and then to predict the rise in cylinder 2. Now, of course, you all know the answer, but what do you think they said? The final water level, this is the right answer, the final water level is the same, and incorrectly, 50% of K-6 teachers and 80% of students in the algebra-based physics course. And apparently, to use a simplistic way of phrasing it, they couldn't tell mass from volume. And this is sad. I mean, after algebra-based physics, it's sad. Now, what would they say if you asked them? Mass is the amount of matter in an object. Volume is the amount of space it occupies. Useless. So in physics by inquiry, students formulate operational definitions. What do you have to do? And what do I have to do? So we know we're talking about the same thing. Let's say you're across the country. That mass is the mass of the unknown object. The mass of the unknown object is the number of standard mass units that balance the object on an equal arm balance. Then if we both do that, we know what the masses are the same. The volume of an object, the number of standard cubes that fit inside, or the amount of water displaced when the object is submerged. Those are the procedures, and that's what an operational definition is. Now, actually, if you ask, I'm not exaggerating too much. What will happen if you're formula bound is density m over v, or is it v over m? How do we motivate them to make the right choice? For each object, they record the number obtained when the mass is divided by the volume. By now, they have the operational definitions for these. They observe they obtain approximately the same number for all objects made of particular materials. They're guided to interpret the ratio m divided by v as the number of units in the numerator, mass, for each unit in the denominator. Only after they have correctly interpreted the quantity m divided by v is the name density introduced. And one of the things that Arnold-Ahrens always like to say, and I like, is idea first, name afterwards. So I'm giving you another example, sinking and floating. The effect of changing mass, volume, and density of objects by examining sinking and floating behavior. They arrive at Archimedes' principle, which I will state, through their experiments. A floating body displaces a volume of liquid that is equal to its weight. And you know, when you look at it this way, it makes enormous sense. And the story, as many of you have heard, is that when he realized that, he jumped out of the bathtub, it is said, and ran naked through the streets of Syracuse, a Greek colony in Sicily. Because it's obvious when you look at it that way, but it is not obvious if you don't look at it that way. So teachers are guided to do this. Now I want to show you what they're working with. Copy the teacher's guide. Example from teacher's guide. This is part of the K through 6 probably curriculum. Two of the characteristics that affect floating and sinking are easily measured: weight and size of objects. For instance, a ship doesn't float because it is light, rather it floats because its weight and size act together so that the water or other liquid it is floating in pushes up on the ship with a force equal to the force of gravity pulling down on it. The upward push of the water depends on the amount of space the ship occupies underwater and is called the buoyant force. Now, these teachers usually have never heard of buoyant force before. And this is for kids. When I say kids, I'm saying K through 6. And it's not helpful. It's not treated in courses that elementary school teachers take unless they take those courses from us or people like us. So here's another question to assess understanding of Archimedes' principle. Administered after instruction. Students told 5 blocks have the same size and shape. Masses increase M1 to M5. Each block is held halfway down in an aquarium and released. The final positions of blocks 2 and 5 are shown. assume the water is incompressible, and it is in small amounts. Sketch the final position of blocks 1, 3, and 4 and explain your reasoning. So 25% correct. This is, I think, the algebra-based course, but I don't remember if it was the calculus-based course. Both diagrams at right can be considered correct. Okay, one's floating, and one is just barely floating, and 2 are denser and drop to the bottom. 3 could be, okay, either way. You didn't have to have them in the right place. You just had to recognize that 4 and 5 sink. Okay, and common correct response was, look, this is what they're going to do. They can go 1, 2, 3, 4, 5. And 75%, it was the algebra-based course. It's inconsistent for Archimedes' principle buoyant force. It is equal to the weight of water. You know, I forgot to say he ran through the streets saying Eureka, or in Greek, Eureka. This is the legend. Elementary teachers who had studied sinking and floating through phrenological approach in physics did much better, 100% correct. And that's what we found. Now I want to show you something else. The common idea is let's inspire students by telling them about complex physics. So the physicist whose name we've carefully removed here, this is from the cover of Physics Today, sent to 40,000 physicists around the world, September 1991. He's very nice. He's getting along with the kids. He demonstrates the conversion of thermal to mechanical energy for a group of third graders. And then goes on to explain about a shaped memory wire and blah, etc. And people, you know, they can like him, and that's good. How could you not like him? He's very, very nice. But that's not going to make people understand physics, something like this. But that's what some of the outreach does. So bringing cutting-edge science to pre-college students may promote interest in science for some students, but they're inadequate for sustaining interest because they don't provide the support that K-12 teachers need to be able to teach science effectively. The people who designed a lot of the materials that are being used were physicists, good ones, and chemists and other scientists. And what they felt is that if you have good materials, they'll teach themselves. And moreover, the teachers will learn along with their students. The belief was the teachers and the students in the classroom would be learning together. It didn't work. So here's another one. Here's a baseball bat, and students shown the balanced bat mass. Compare the total mass to the left and right. This one's a little harder, but the mass to the right of the fulcrum is greater because you have to realize that the distance from the fulcrum matters for the turning, and it depends on both mass and distance. And the percent correct, 5%, sorry, I exaggerated by a lot. 5% of in-service teachers, many of whom have taught balancing. Balancing is in the has been in the basic elementary curriculum. And introductory calculus-based physics, of course we've taught them that. But guess what happened? The masses are equal since the center of mass is defined by them, where the mass is equal on both sides. That's a literal interpretation of the word, of the words. And I like this. Give me a lever long enough and a fulcrum on which to balance it, and I shall move the world. And that's a statement by Archimedes, and I think it's very profound. Another example, and I'm just passing through this quickly, because another thing taught in elementary school is naked eye astronomy. So a couple mistaken beliefs. The sun rises and sets at the same positions each day. The moon phases are due to the Earth's shadow. I'm telling you, this is what is commonly believed. So astronomy by sight guides students in making naked eye observations that help them infer the shape and motion of the Earth and account for the seasons, moon phases, and eclipses of the sun and moon by what they observe. Now, this is another aside. Our group probably owes the fact that we have north, east, south, and west exposures of our labs because we make shadow plots of the sun. As whatever the reason was, we got them and we really like them. I did not imagine that Jim Evans, who is with us tonight, who led the development of the astronomy module, would study ancient Greek as part of his research. When he handed me his dissertation, 2 thick volumes like that, I said, Jim, there has to be another one, an introduction, because I couldn't envision reading all of that carefully. And it led to a book, and now he's involved to some degree in the Antikythera mechanism, which you read about, some of you read about, in the Seattle Times on December 31st. So that was very nice. Now, one of the problems is if you help teachers and then you dump them, something else comes up to attract their interest. We have an annual 6-week summer institute partially funded by NSF for in-service K-12 teachers. And we recognize that in order to keep their interest, we needed to provide a place for them to come. Many of them, there's only one in high school, only one physics teacher to a school. They don't have colleagues. So what we do one night a week is we have them, they come over, they meet with one another. Many of them are just one teacher in the school, as I mentioned. They take turns bringing dinner, but it's really serious. And they help one another. And the interesting thing is the kindergarten to the high school teachers, they get along, and it's been a good thing. Unfortunately, however, you have to do something like that because none of the programs that I listed earlier, you probably don't remember, the Seattle Local Systemic Change Initiative we were in, the local school district dropped it as soon as the federal funding ran out. So our initial focus was on K-12 teacher preparation. We started examining student learning in introductory physics courses. On certain types of qualitative questions, it didn't matter before or after. Calculus-based, algebra-based, descriptive didn't matter. With and without demonstrations didn't matter. With and without standard laboratory didn't matter. Large and non-uncertain kinds of questions, and regardless of the popularity and the structure. So these things have little effect on student learning. They may have an effect on student liking, and they certainly have an effect on evaluations, course evaluations, in many cases. But, so the question is what to do? These are large classes, they cover a lot of material, they go very fast. How do we get the students to be engaged? And we had to pick something doable in a department like ours especially. What could we do? It wouldn't be revolution. Revolution would never work. So we had to recognize the constraints imposed by lecture-based courses, and we developed research-based tutorials that grew out of our experience of physics by inquiry. So the provost at the time, Laura Wilkening, was there just in time. She offered financial support to improve instruction in introductory science courses and asked physics, chemistry, mathematics, and psychology to submit proposals. I won't go into the details, but ours was funded right away, but they didn't tell us. They waited till the others had submitted adequate proposals. They told all 4 of us at the same time. The first suggestion that was made, let's go back to recitation sections once a week and problem solving, and there'd be probably mini lectures by TAs, that's what happens often. And the final proposal, which was accepted, was by us, introduce weekly 50-minute tutorials developed by our group to emphasize qualitative reasoning. In-depth preparation of the TAs would be required. Qualitative questions be a significant part of every exam. Now, is a standard presentation of a topic in textbook and lecture adequate to develop a functional understanding? If not, what can be done? And so the tutorials emphasize the concepts, the reasoning ability, and the relating of physics formalism to the real world, not practice in solving quantitative problems. Now, you might be worried, my gosh, what happens to them on quantitative problems if they're not? You know what? They do at least as well. It doesn't matter. The fact that they understand the material better is what makes the difference. So I'm going to give you another example. This one is in both physics by inquiry and tutorials. The students could solve end of chapter circuit, I = V over R, that kind of thing. They could do that. What they couldn't do, I'm going to let you have half a minute to decide. The batteries are identical and ideal. Rank the bulbs from brightest to dimmest. And I'm going to give you the answer because there isn't time to do it. A is as bright as D, is as bright as E, both brighter than B = C. Now, you can, as you will see, you can give this to students who know the formalism, not that the formalism is appropriate in this case, they're not ohmic resistors, but it gives you the right answer. But anybody who has a good model can look at that and answer it very quickly. And so 15% in the calculus-based physics course, over 1,000 students at the time, high school physics teachers, university faculty in other sciences and mathematics, I want to make that clear, graduate TAs and postdocs at that time, 70%. And it didn't matter whether or not these questions were asked before or after instruction in a standard lecture course. Persistent difficulties, the belief, the incorrect belief that the battery is a constant current source, and the belief that current is used up in a circuit. Now, if you haven't had physics, this may not make a whole lot of sense to you, but if you address those difficulties, it turns out that almost everybody can do similar problems correctly. And the basic underlying difficulty is they had no model. It was just the formulas. So I want to comment what some people say, it's just a misconception. The trouble is, it trivializes the problem. You can't solve misconceptions independently and think you've gotten anywhere. So how we do it, there really isn't time to go into it. We help them construct a conceptual model for an electric circuit through hands-on experience with batteries and bulbs. That's now done in our labs. Questions that require qualitative reasoning and verbal explanations help them develop a functional understanding through their own intellectual effort. And we are aware of what the errors they're going to make are, and we explicitly address them by asking questions. Here is a post-test. I should mention post-tests are on final exams. And bulbs A, B, C, and D are identical. Rank the bulbs, and the correct response, which we haven't got time for me to give you the time, A equal D, brighter than B equals C. Results, 75% correct compared to 15% on the pretest. Elementary school teachers who have spent more time on this are at 100% level. It takes time. Now, we haven't got the kind of time in the kind of courses we're teaching in the department for that much. So, however, what is important and what we've come to, that we make a real point of, is that the TAs need to address the difficulties and they need to overcome to teach as what has been taught. They are required to attend a preparation every week. It is required. And when do we quit trying to be perfect? Well, when the introductory students on the post-test, the exams, match or surpass the pre-test performance of the TAs. That's our criterion. Otherwise, you could go on forever and maybe never get 100%. So I want to comment a few more comments. Curriculum in both is research-based, which I gave you examples of, and research validated. Every textbook that is published nowadays says it's research-based. Just because it's research-based doesn't mean that the strategies that have been put into it are research validated. So they have to be validated or we don't consider it, in our case, research-based. Now, there's a need for additional research we haven't dwelled on, and other people have, related to computers, clicker questions, flipped classrooms, and MOOCs. You must have read about MOOCs all over the world. Now, how do they assess these things if they get to the point of assessing them? They're multiple choice, standard tests, but they don't give you feedback on what you need to do to get a better result. So promoting change in instruction requires access to students. You have to be in a physics department to have access to students, except I'm not saying occasionally, but if you want ready, constant feedback, you have to be in a department. The faculty have to accept this, and the credibility that has to be recognized by traditional measures in the academic physics community, publication, talks, etc. But you have to take into account the culture of the department. If the department won't accept this, it's not going to work. So it requires deep knowledge of the subject, ready access to students, formal responsibility for instruction. Only faculty in physics or science departments typically meet all these requirements and more likely able to influence other faculty. So here's what I think is very important. Perhaps the most important contribution that courses in introductory physics and in teacher preparation can make is the development of scientific reasoning ability. So it's the reasoning, and I have the belief that it is the most important, really the most important thing that you can do for most students who take that course is help them develop the ability to reason. It requires a dedicated effort and cannot be done quickly, but it can stay with you. And the study of science should help develop ability, it's obvious almost, in scientific thinking, critical thinking. And by what do I mean by reflective thinking? Learning to ask the types of questions necessary for recognizing that they do or do not understand. Learning to ask the types of questions necessary to develop an understanding. And these goals transcend the study of physics or any science. So now I want to just a few more comments. The achievements of our group are made possible by ongoing support from NSF, the University of Washington, and the Physics Department. National Science Foundation has funded our summer institutes and to some degree our academic year continuation courses, and our research and curriculum development, PBI, Physics by Inquiry, and tutorials in introductory physics are really the results of NSF support. The Physics Department and the University of Washington, our department has cooperated, and individual faculty have, in many cases, been very helpful. The commitment of the administration, especially the College of Arts and Sciences, to promote improvement in undergraduate education and K-12 teacher preparation, and we have 3 tenured faculty positions devoted to physics education research. It is my hope that the UW will continue to recognize the need for discipline-based education research and to foster groups like ours through regular faculty positions in physics and other sciences. And boy, I made it.
Perfect.
Thank you very much.
I want to thank Professor McDermott for a fascinating and, in my case, humbling lecture. I got precisely 2 of those questions right, the first one and the second to last one. Everything else proved why I'm a medieval historian. I also want to thank her because it's always an honor to share a stage, in my case, however briefly, with someone who is a true pioneer. A pioneer not only in her chosen field of physics, but also, as she alluded to very briefly, in being one of the very earliest people to break down the anti-nepotism rules. And speaking very personally, as someone who would not be here at all had those anti-nepotism rules continued, I have a personal reason to say thank you for that as well. So please join us upstairs in the Walker Ames room for some refreshments and a chance to talk more with Lillian McDermott. And thank you all for being here.